crystal is electrically switched to color, and then can make a full color display without multiple layer. And also doing some of this single layer color photo-tuned color pixel for bistable device. So I kind of give switch the gears a little bit towards this application, but we go from the fundamental, what makes this work. And well, in the end, if I get too much time, I've gone through these slides too fast, and I show a little bit different kind of flavor, such as our recent work in lacing in this electrically tunable lacing in this cholesteric, and also this electrically switchable colors in blue phase, full range. So let's just see. So I heard that Oleg told me that earlier liquid crystal discovery, not just before this the next person, everybody know this Renaissance. So cholesteric is one of the important material being discovered. But I heard that there are other researchers such as the planar of this institute, also was part of that observation of this cholesterol derivatives about this freezing point. I had some kind of this color effects and also two melting, but didn't publish. So I guess this Renis published this and talking to a physicist from Germany. And so the material is like this. It's a cholesterol derivative. You can see on this part is the cholesterol, and then that's the kind of acetate from benzoyl acetate. So that's why it's called cholesterol, benzoate, and then melting at this 145 degree, and then become cloudy, but it doesn't turn clear liquid. So until 178.5 degree, this material turns clear under the polarized light, by this circular polarized light. But in addition to that, you can rotate this planar polarization of this light, of this incoming light, not just only rotate, but also transmit one the other component. So it separates the lights into two circular polarization components. So that's the kind of physicists involved in this discovery. So I think most people now recognize this is a Renitzer, botanist, and this physicist discovery. But I think there are others. So if you know some other people in this area, you may want to just continue to tell the story. So that's my stories here. Looks like this. In general, all kind of cholesterol materials. If you are changing the structures, you can change this transition temperature a little bit. And then on the other hand, for application, all the cholesteric liquid crystal materials for device application probably been explored almost 40 years ago, at the end of the 60s. So this is almost 2010. That's why you can see that's almost 40 years back. People knows all the effects. Unfortunately, by the time the material, sorry about that. Unfortunately, the material in the past used for those discovery is either high viscosity or monocomponent, no room temperature effect. Later on, people, I think, discovered this cyanobiphenyl, and his name is George Gray from England, and then with these chemistries that enable to producing some kind of stable materials under the temperature cycling. And then in addition to that is if the material do a little bit modification, introducing an optically active components into the molecule, and make it kind of physically that can rotate these molecules if it's in the order. So forming this induced cholesteric device materials, and then if this materials is kind of somewhat oriented in a plane with this director in one direction, and then by the surface control the anisotropy, and then this material may be adopt this kind of helical structures, and with this helicity, it depends on this chirality of this dopant and the concentration of the dopant. So you can tune the helical pitch at any at your wheel. So if you are kind of choosing to refract in to formulate this cholesteric material in the wavelengths of light, in that case that you can see that the iridescent colors are coming out from this material. If it's misaligned, then you can see multiple colors. Okay, and this material normally has an angular dependence of this refraction. So the cholesteric pitch and twist head sense, I think, has been explored. It's very easy to find information if you go to this DGEM's book. You can find this induced cholesteric. This helix, if you are dissolving one chiral molecule into a host, pneumatic host. In that case, that you can form this kind of structure that with helicals is a distortion. So that distortion energy is regularly can be defined by this Frank energy of this distortion. And in this case, that since the twist turn is the major component, so this free energy can be reduced to just a simple term related to this twist elastic constant. And then you can determine that handedness either right-handed or left-handed depends on this rotation of this theta with respect to this helix axis. So if it's rotated counterclockwise by these mathematical terms, and then you can define that as a right-handed or define that as left-handed. But those are kind of basic, regardless of their handedness, this Bragg refraction, the wavelengths selected by this material that you formulate, it will be the same, except it's just they rotate different planar polarized light. So that's kind of a common background for mathematical expression on this cholesteric pitch and twist sense. Well, so you have the material, you need to determine that physically. So you can use multiple methods. One of the methods is using this the wedge cell. So if you have wedge cell, then surface you coated a layer of this alignment materials, such as a thin layer of polymer. It could be polyimide, it could be any polyvinyl alcohol. And then you rub them, and then you assemble this cell with the fixed spaces. Then you will know that what kind of cell gaps that you will have. From this kind of structure, you can determine that. But if you put this into the microscope, then you can see those periodicity of different kind of discrimination line. So between those two lines, then you have half a pitch length, and so with that, you can measure that what's the helical pitch of this material. So since you know that concentration, how much of the additive you put into the pneumatic, and then you will know that you will know the helical pitch. And in some sense, that if you use other methods, then you can determine the helical twisting power. The reason that we go through this is tunable colors. What we are doing is we are adjusting the helical pitch. So that's the reason that we need to learn a little bit about the basic before we know that we get the color changed, in addition to just observation. Okay, so here is the Bragg refraction. If you put them into a cell and with the helical axis perpendicular to the substrate, and then at the no applied voltage condition, 0 volts condition, and this helix is supposed to form a very perfect alignment, and then you will have some kind of issue of this angular dependence, which means that at the optic angles you see different kind of helical pitch with respect to that, as a cosine theta effect. So the wider the angle you have, the shorter the pitch. So that's kind of angular dependence that everybody knows on this cholesteric material. But in the case, if you have some phases beneath this cholesteric, such as this somatic A phase, this material you can buy this. Actually, they have a formula. It's called TM mixture. TM mixtures 74, 75 A or B, and they have different kind of temperature range. And in this case, the helical pitch is kind of going into the infinity. In that case, so you will have at a lower temperature, this if you formulate this material in the visible range, you will see the color change from short wavelengths to long wavelengths. But on the opposite, if you have regular materials, they are kind of temperature dependent on their helical pitch for one single component. So that's kind of this phenomenon is also known, quite well known because people using this for these thermometers, for sensors, detectors in the past for medical, even trying to use that for medical imaging. So you see that they have two different characteristics. So what we will do is when you have this kind of structures, you also have a defects structure. The defects comes from different kind, depends on the orientation of those helical axes and then in the cell. In the case that you have a very good alignment, and then you can have generate some kind of very few defects. But if you have a poor alignment, then you have more these discrimination lines, and then you can use this simulation to study this fingerprint twister. These are +1, -1 defects, And this is tau 1, the tau half, and then this ±1/2 defects. But in some cases, you also have this photonic, right? It's a random domain. How do you do it? When you put in the nanoparticles into this cholesteric, it is disrupting this orientation. Or you put in some polymers in there, and then you also disrupt in some orientation. And you can have these photonic structures. So in that case, that their optical property is slightly different. One is you can show some uniform Bragg refraction and with selected wavelengths. The other is just kind of randomly weak transmissions of the light and sometimes scattering, weak scattering inside of cells. So those are the optical properties. But what happens if you, since you have obtained one of this material that allow you to apply electric field, because the material now has a positive dielectric anisotropy. In that case, that you can either unwind them, but if you turn the field off and in different kind of condition, you ramp it, or instead of you just cut it off. So this response of this cholesteric materials is quite different. So you can have this kind of two different kind of states, either it's a refractive state or this transmissive state. So the field turn off very quickly or slowly, and we can see from this picture. If you turn off slowly, you kind of disrupt in this orientation, and there's a kind of a photonic texture. So in that case, that you also can recycle this to eliminate defects. The other one is turn the field off very quickly, and then you can see that from this orientation to homotropic to a planar state. And so this kind of a field depends on the materials that you're using. The dielectric anisotropies of the materials. If you increase that, you can lower that critical fields. Okay, so we're talking about this cholesteric. The basic usage is the color in the visible range. Certainly, they are also useful range, like in the UV, in the infrared, and depends on your application. They could be used as kind of switchable filters for this optical communications using this 1.55 microns lasers. So in general, this type of device, because they use the Bragg refraction, if you use that for this kind of electronic reader, nowadays you go on Google and you see that Kindle is on the front page. Okay, but Kindle uses different kind of approach. Kindle uses particle type of this device, and then the cholesteric using liquid crystal. So we kind of focus on this cholesteric in this case. In general, the refractive type displays are sunlight readable. They are high contrast and they're flexible. You can put them on this plastic substrate. So nowadays, the next generation future trend of this liquid crystal device will become more like flexible like a paper. Okay, you can fold them up like origami. The more like Japanese arts, you can paper arts. You can fold them in different kind of shape. Put it into your mobile phones. And they could be very rugged and robust because they put on a plastic substrate. You can reshape them, and they can suitable for roll-to-roll manufacturing. They compatible with available display manufacturing line, and they can also change the shape and type depends on the design. Well, that comes from the application usage of that. It could be bent ones, conformal display, or this retractable, rollable. That means that they have to sustain this multiple bends. In that case, that some of the art device, if you're a good artist, you can create this kind of shape and size, whatever you want it. So those are the advantage. So we will focus on this cholesteric, how to generate color, right? For color, I think one of this cholesteric material that you selected, generate only one color. But you know how to generate multiple color, either using this sequential color pixels or this stacked color panel. You know. So in the stacked one, you have to use 3 separate ones, and then but it's a sequential color, just like our computer screen with color filters behind it. So for cholesteric, sometimes require more work than just using color filter. In that case, that you can use the stacked layers. That you can have a blue, green, red, and stack them up and using this multiple colors device. And then on a flexible substrate, you can achieve the goal that you wish to have. But that requires when you bend in 2 substrates, that requires some kind of structural support. Otherwise, they will fall apart. The cell gap will become inhomogeneous, and then you will have this poor contrast. So the one way is to using polymer to kind of using the binder to tighten up and down together. Well, certainly putting polymer, that's another heterogeneous species, and then you have to control their phase separation process. So depends on where they are, and then you have to carefully, otherwise they will give you a high switching voltage and moderate contrast, deteriorating your performance. Although they have plenty of kind of advantage, such as you can use that for continuous roll-to-roll, no polarizer require, light transmittance, mechanical stability, and so on and so forth. But that's the problem. Here, I give you one example. The one of this is, you mix in polymer with this cholesteric liquid crystal with this light, wavelengths of the light gets selected to reflect the blue, and you add in some kind of tunable chiral dopant, and you can use the light to tune the color, okay? And hopefully this one, you can, if you want to have a full color, you wish to have this color stays, and then so you can tune this color become irreversible. On the other hand, you can also choose that material that allow you to kind of reversibly change the color back to the original. That's kind of a process. So in general, this type of device, you can start with in responding to the applied fields, you can start from this refractive state, or it can be switched from to this transmittive state. And this low transmissions until some of this critical voltage, and then this texture started to respond to applied field. And you can see the colors change as a function of the applied field. On the other hand, you can also start from this refractive state and switch them to this different state. These photonic textures allow some of the light transmission scattering, and so you don't see the reflectivity. And then there's some higher voltage on one helix that you put in the pulse back to this cholesteric. So they're responding, instead of going to photonic, they're going back to the planar texture. So that type of device is kind of interesting. The only disadvantage is higher voltage. So here is one of the issues here. The other one is we saw that this multi-layer stacking. That multi-layer stacking can be used for this generate 4 color, but it requires 3-layer stack. So if you want to stack 3 layers in general, you will have 6 substrates, right? So to eliminate those substrates, there's a way to do that is to use this continuous coating. This coating process you can either use in lamination. So in this case, the substrate can be anything. What you need to do is you just need to have a kind of planarization layer, and then you coat it on this conductive electrodes, and you put it on this cholesteric material. Once they phase separate, and then you can continue to put on another layer of electrodes, and then put on this separation layer or protection layer. So if you repeat this process for 3 times, then you can have 3 different layers of color material. Phase separated polymers, you can see that if you have a polymer concentration roughly around 20-something%, for example, here is 23, and here is 25, and here is an increase in the polymer concentration. So you can see that, well, once they phase separate, they look like cheese-like. Okay, the cheese-like is you're trying to control the size of the cheese. In that case, that you get to maximize this reflectivity, minimize this loss in the scattering. On the other hand, is you also want to have some kind of protection layers on top of it. So if you can use in this light-induced anisotropy phase separation to make the phase separate polymer stays on top of the layer instead of the bottom or everywhere. So you can see that over here on the top of the layer, this is thicker with the polymer. So that's kind of a phase separation process with this morphology for this type of device. And that device it's kind of stacked with 3 different layers and some of this conductive polymers layers electrodes get fabricated in between the layers, so you can minimize that. That's one area. Well, recently, if you see this Fujitsu, you see you go to YouTube, you type in this flapia. The flapia, they will show you that this type of device has been fabricated into electronic book, electronic readers, and that this type of device using in general using 3 layers of this phase separated polymers structures, and then those cholesteric get encapsulated. Kind of a microsphere, and they are in the range of a few microns, 2-3 microns to about 5 micron size. And in that case, that you stack them, and then you're using 3 drivers. So talking about this is kind of more like disadvantage of using this type of stacking device, because first of all, it increase the cost, increase the weight, and increase the complexities in switching this type of device. So here's some more work that we think is possible. Maybe instead of using 3 layers, we're using 1 layer only. And 1 layer is we use electric field applied across this device, and then to switch them. So the helix in this in the bulk either tilted or get compressed. And then, so you can, in that case, that you can change this original reflective wavelengths. But this is not new either. In that case, that you may see, well, because people have learned this already when in the long term, a long time ago, when they are using this cholesteric material, they already knew that it is possible responding to different kind of light field. As early as 66, you see that Harvard already knew that the voltage effect in this across the field. In the 70s, they also have this very common, and also different people that using different kind of applications or methods to try to achieve the goal. They can tune the materials to a wider range. But in general, there are 2 common phenomena that they have observed. One is they are unable to tune the wavelengths to a wider range to cover whatever they are trying to achieve. The second thing is they have to use extremely high voltage and destroy the material. Certainly, there are more factors of that, and some people using the in-plane fields electrodes with on one substrate, and then the other substrate is no field. So they were trying to unwind that helix with a crossover electric field, in that case, that also has lots of issues, the slow response, and there's need a very high voltage. Okay, so we think about that instead of electric field, we'll see if we can use some material to put it into this polymers. So when you before this apply the field to unwinding this helix, we kind of using the heterogeneous materials to confine them, and so holding them up. So with that, there are several approaches, to use this. You can put in all kind of stuff to put in there, but in this case, it looks like polymer. If you kind of lightly crossing them, and then with appropriate amount, you are able to confine those pitch extensions, and then before they really fully extended, and then you can shift the color of the Bragg reflection. But here's one example. If you have only liquid crystal, you apply the electric field across the cells, and you can put in place this Bragg reflection wavelengths into a different wavelengths. But that's only a small shift. But when you continue to increase the voltage, you kind of twist unwinding that helix. So the Bragg reflection peak disappears. In this case, you don't see any. On the other hand, if you put in some thin layers of polymer, like what I just shown you, they phase separate into kind of localized on one layer. So not too much in the bulk in between the two substrates. In this case, you're able to apply the fields a little bit longer, higher, and then the phase shifts, the Bragg refraction wavelengths can be shifted a little bit wider before it gets totally unwind. But in this case, it's kind of interesting. If you put in the polymer in the bulk compared to putting polymer on the one layer, one substrate surface, the interesting thing is you see here is anisotropic refraction and transmission on one substrate, and the others doesn't only refract the light. And then certainly the Bragg refraction wavelengths and reflectivity is a function of applied voltage in this case. So this color convertivity of this device shows that they are reversible in general. You can switch them to different colors, and then they can show this. So you want to study how fast this material can be switched, change the color. There's a way to do it. In general, they roughly around rise and decay roughly around totally in the range of about 30 milliseconds, which is very good enough for this just for electronic readers to change this pixel or this the images on the display. So here just show you that on one side with polymer network it really shows only Bragg reflection can be continuous tuned, and then the other side is doesn't reflect any light. So to prove that is there's one way to do it is you using different kind of pulse width and also this arrangement of your detectors to show that. So here's the oscilloscope that shows that if you apply the lower voltage, that's to that crossover, and because this is the helium neon laser light, 633 nanometer. So this material is interesting, different from the unwinding the helix. Instead, with a very small amount of polymer network, it induced this blue shift. Instead of unwinding, it kind of shortening this helical pitch before they totally get unwind by the high field. So here is like this. You have a refraction, and then if a reflected light, that's transmitted light, and you apply the field, and then it shifts away, so transmitted lights get lower, and then but the transmitted light is slightly increased. That really depends on how far you shift these Bragg reflection wavelengths. And once you shift away, shift to the wavelengths of these laser lights, and then for example, it starts from 650 nanometer to 630, and then you can see this slightly increase in refractive wavelengths of light, and because of the detector a little bit. But if you use a high field, make it shift faster, and you can see that the Bragg refractions recovers a little bit faster, and then it kind of decay a little bit, settle down because backflow in that case. But for this transmittive sites, once you shift the weight, all the refractive light intensity kind of get decreased. So you don't see any response from that this detector, regardless is the low wavelengths or high wavelengths, low voltage or high voltage. Well, with this type of materials, this device become this kind of less temperature dependent, and then until to this isotropic temperature of the cholesteric material, and then you're losing this, and that's the switch of the device color. You can see just apply the fields, and you can shift a little bit. On the other hand, since these materials respond to the frequency of applied voltage slightly different, depends on this the dielectric anisotropy. You kind of shrinking of that range as you increase in the applied frequency. So, in general, with that kind of characteristic, you can also use in this wavelength, this frequency to tune these colors. Instead, you can change that from blue to red or red to blue by applying the different kind of either voltage or frequency. So that allows you additional methods to program this optical tune the colors. That means you apply the voltage to change to blue, and then you can shift it back with changing the frequency, and then they will rotate. They will move this Bragg refracted wavelengths to the longer wavelengths. So that gives you one additional options here. So I just kind of skip on over here. You can see the diagram here. Well, if you apply the voltage and then higher voltage exceeds some of the critical voltage, then they become on the top it become black. But if you kind of lower that voltage or change it to the different kind of frequency, and in that case that you can switch them back from this dark state, light transmitting state to a color refraction state. So once you get into some critical point regions, this planar region, but in between you also have some kind of induced flow because of ions, and then you will have this photonic state and low reflectivity. So it's a little bit more complicated here with the frequency driving. So electric tuning is kind of interesting because it's convenient by the electrode patterning. The other sensors, let's take a look. People are interested in this security sensors type of device. So here we are showing this using light to tune the color pixels, and light which can be used to adjust this helical pitch. But you need to one assistance coming from this additive of this, such as tunable chiral dopant. This tunable chiral dopant, they should have this functionality. They should have this ability to change the sign of their chirality, which means that your helical twisting sense of cholesteric will change the sign from right hand to left hand, okay, or right hand to no chiral. So you lose this chirality, become pneumatic. On the other hand, you can use this different kind of molecules. They may rotate their chiral helical axis, and then chiral axis, and then change from the clockwise to counterclockwise. The other is just conformation change, and this is well known that people using this azobenzene, they can change from the O trans to cis, or this cis to trans. And then in that case, this chirality actually is not changed. They just change the conformation. So from this aligned state, they have a helical twisting power because of the interaction between this chiral additive molecule and this pneumatic host. But in that case, once they disrupting this, they change this density of the material because the volume of this molecule increase. And in that case, that the interaction between this chiral additive molecule and your pneumaticals become decreased. And in this case, that you will change this helical twisting power beta here, but you are not changing the concentration. Okay, so the pitch is kind of that. So I guess we're kind of trying to speed up here. Well, there are also prior work, quite a few prior work. In this case, the 2003 there's a paper using this material. You can use the light to change the shape, and therefore your absorptions can be studied by decreasing in one area and increasing in one area. You can see that they can shift this color. That's very straightforward. But in our case, that we want the color states instead of reversible. So in this case, we use thicker material, and this material has some characteristics that allow you to change it reversibly. And then so you make the dopants very small quantity, and you can shift this bandwidth even back and forth, left to right or right to left, depends on what you formulate. First of all, you need to use some kind of boundary, more like a partition. You need to create some area walls, and then you can tune that colors from blue to blue to blue green and to blue green and red. So here's the color pixels. So you can see you can tune back and forth, depends on what kind of formulation you use. For color pixel, it's the single substrate can be tuned. And here is kind of electro-optics effect, just like the previous one I showed you. You can be switched from the refractive state or this transmittive state. But because of the materials are different, with the lower pyrodopant here, the switching voltage is much lower, about 32, but for blue is much higher. So there's a differential, switching voltage. But this can be accomplished overcome by this engineering method. We can talk about this later, or I can give that to your question. So I guess I thought I might have more time to talk. The bistable device I've shown you here, I have a 3-panel stacking possible. It's a single panel with photo-tune of this electrically tuned. And with that, I will be open to your question. But if you are interested in more or different topics, then we can continue.
Thank you. Thank you very much. Although there is not much time, but some few questions, please.
I'm just wondering, what is response time to your switching to different pitches when you illuminate the UV light? How fast you can?
For the last topics, the photo-tuned color pitch pixel, the response time just like regular is cholesteric materials. It can be in a few tenths of milliseconds. Maybe
What I mean, the pitch is changing, which is macroscopic parameter, and then the relaxation time should be very, very large. What I cannot understand how it can change pitch very fast. That's my question.
Okay, now I got your point. In this type of materials, it takes seconds, tens of seconds, 26, depends on the intensity and dosage of your UV light. For this switchable device, it takes at least, I would say, 10 seconds, to completely switch from one pixel, one color to the other.
I have another question. What is the difference in time between direct response and then the factor of relaxation? You illuminate, you have transition, change the pitch, let's say for 10 seconds. When you stop, when you cease illumination, how fast it relaxes back? Same 10 seconds.
You mean like this? The intensity of the light and the function of the...
I mean, you said the relaxation time is 10 seconds when you illuminate.
Yeah.
When you cease illuminating, you relax back to the initial pitch. I'm asking, what is the relaxation time? Was it to the initial state? Same?
Oh, to the initial state, same, yeah.
Same.
Yeah. For those, for this type of photo-tuned colors, they are very slow. You know, they are useful for like maybe scanners. You could put in the scanners and then they scan the image on top of that, and you can stay for a certain amount of time. Because this one is more susceptible to environmental change, like temperature.
Okay, let's